Welcome to Electron Line, and here's a very interesting application of the effect of moving charges in a magnetic field. And this was done by Thompson, where in 1897 in England he determined how to calculate the ratio of the charge in an electron divided by the mass of an electron, so the E to M ratio. And this was done in this apparatus, which was encased in glass and highly evacuated, so there's almost no air inside this tube here. This was a glass container. And here we had a cathode, and the cathode which ejected electrons in the direction to the right, and then they were passing through a set of plates over which we had a potential difference. And so on this side we had this plate positive, this plate negative, and so there was an electric field from the positive to the negative, and of course electrons feel the effect of the electric field and would be accelerated through the electric field when they emerge on the other side. They would be moving at a pretty high velocity at that point. And then they move to this region right here where they would be subjected to both a magnetic field and an electric field. And that would then act like a velocity selector. Notice that the direction of the force felt by the electric field would be from top to bottom. And there you can see that any negative charge would be attracted towards the top, and so there would be a force in this direction due to the electric field present. And then using a left-hand rule, notice that the electrons would be traveling this direction. That's the direction of the fingers. Then we turn our hand to show the direction of the magnetic field, which is into the board, and then our thumb shows the direction of the magnetic field force, the force due to B field, and that would be down, so it would be compensating for the electric field force pointing to the top. So electrons would feel a force in this direction, would feel a force in this direction, and then only certain electrons with a specific velocity where the two forces would match would then go straight and form a little signal here on the screen where they could be seen. From that, he was able to calculate the actual ratio of the electric field of the charge strength to the mass of each electron. And let's see how that came out. First of all, the velocity was determined by how fast it would be moving when they passed this particular point right here. We can say that the kinetic energy gained by moving from there to there is equal to the potential difference times the charge on the electron. So that's a known equation. We know that the kinetic energy is always equal to potential difference times the charge. And so from that, we can say that the kinetic energy would be 1/2 mv squared. And I shouldn't use a big V, I should use a small v to differentiate from the voltage. So 1/2 mv squared, which is equal to the change in the potential difference across these plates, times the charge on each electron. Let's just call it E, because the charge in each electron is E. At the same time, we also can say that the velocity of the electrons that get past this point could be determined by setting the force of the magnetic field equal to the force of the electric field on the electrons. And for the magnetic field, that would be QVB, and for the electric field, it would be the charge times the electric field strength, QE. And then you notice, of course, that the Q's cancel on both sides, so then you can say that the velocity is equal to the ratio of the electric field strength divided by the magnetic field strength. Of course, the magnetic field strength would be known, and the electric field strength would be adjustable so that we would know what velocity the electrons would have that actually make it through to this point right there. Any electrons that move too fast would feel a stronger velocity, a stronger force on the magnetic field, and would curve downward. Any electrons that move too slow would feel not enough force of the magnetic field and would be overpowered by the force of the electric field and would come up here. Only electrons with a certain velocity would make it through and hit this point right here where they could be seen on the screen. So now we're going to solve this for V. We can then say that V squared is equal to 2 times the change in the potential times the electric charge right here divided by the mass. And then we can take the square root of both sides, so we can then say that the velocity is equal to the square root of 2 times the difference in the potential across the plates right here times the electric charge. Actually, you know what I want to do? Probably not the right thing to do this. What I'm trying to do here is set up the ratio of E to M. So let me solve this equation for E over M and move the 2 times the potential difference over here, so I can say that V squared divided by 2 times the potential difference, delta V, is equal to the ratio of E divided by M. Okay, that's what Thompson realized, that this would be the case. And then over here he said I can adjust the velocity by setting it equal to E divided by B. And then if we relate those two equations equal to each other, if we substitute the V over here by E divided by B, we then get the following equation. Then we get E squared divided by B squared times 2 times delta V, that should be delta, times the change of potential across those plates would be equal to E over M. And then finally, of course, by turning it around, we can say that the ratio of E divided by M is equal to the electric field strength over here, squared, divided by 2 times the change in the potential times B squared, like that. Okay, now it turned out, when they calculated that, they got a value, what's interesting, so they got a value of 1.602 e to the 19 minus divided by 9.11 e to the 31 minus equals, this ended up being 1.759 times 10 to the 11th, and of course the ratio would be coulombs for charge divided by kilograms for mass. So what Thompson realized, that the ratio of the charge in coulombs on electrons divided by the mass of the electrons was an enormous 1.759 times 10 to the 11 coulombs per kilograms. For each kilogram of electrons, there would be, and billion is 10 to the 9th, so it would be 176 billion coulombs per kilogram of electrons. So that was the first time ever that people had this relationship between mass and charge on the charged particles called electrons. And that was an enormous experiment and easily done once you understood the principles of the electric field, the magnetic field, and how you can change the kinetic energy of electrons through a potential difference. Very clever, this Thompson, and a very amazing experiment that he came up with, far back in 1897.